All right, hey, what's up, guys? How's it going? All right, so we're back again with another walkthrough of this week's assignment. Today, we're going to be looking at fraud detection. So again, I'm really intending these for beginner types that want some detail in terms of what's going on with some of the code and would be interested in some of my tidbits for tackling some of these issues. So with that said, let's jump into it. All right, so I know last week, either in a video or on Discord, I said to do as much as possible on Google Colab to take away some of the dependency issues and some of the local compute issues. Well, this week the data set was fairly large for this problem, so I actually had to do this work on my local machine, which is fine. So I'll kind of just walk you through that and getting that up and running. So of course you want to use Conda. So once you install Conda, you'll have a command prompt that comes with that initial Conda installation, at least the larger one, and I'm sure the smaller one as well. So pull that up and cd to the directory that you've parked your data in. So let's do that. CD, so I have it in documents. All right. Yep. CD there, and then I think we have it. Let's see, directory CD to week 3. Yep. DRA CD to homework. Okay, and then CD finally to IE fraud detection. Okay, cool. And then here I should have my notebook here that we're going to be walking through. All right, so then once we're here, we're going to want to spin up the Python environment that we created to do this work. So again, the nice thing about Conda is that it allows you to create environments for different types of use cases and projects that you might have. This is key because you're not going to be using the same packages for all of your different projects. Sometimes you'll need different versions, and it's helpful to have these containerized in Conda environments to just make your life easier and also to help with reproducibility. So you want to, if you want to list out what environments you have installed. So so first you have to create an environment. I won't walk through that. You can find that on the web, but you'll create your Conda environment, and then once you do that, you'll find that you'll forget what you called that Conda environment. So you can use Conda environment list, and then that should pull up all of the Conda environments that we have up and running. So here are the ones that I have, and then I want to spin up my Pi3 Conda environment. So Conda activate Pi3. Okay, cool, and then I can see here that that's now activated. So this is my Pi3 Conda environment that I'm going to be using to work on this particular assignment. So now that I have that, now I want to launch my Jupyter notebook. It's actually a JupyterLab notebook, which I've been messing around with. So we do that with JupyterLab, and that should be spinning up. Cool. So that's our kernel here, and here's the notebook we'll walk through. Okay, so let's go through this, and let's just start going through each one of these cells, importing our typical dependencies, and then we're reading in the data that we downloaded from the Kaggle competition. Before we jump into that, I'll also give you a helpful tip. There are a lot of notebooks here, so these are going to be kernels of people or notebooks of other Kaggle competitors that have provided examples and codes and results for their efforts. Highly encourage you to step through a lot of those and to pick out anything that jumps out and kind of help you along. So a lot of good stuff, and it's coded by Python and by R, and all the top ones seem to be Python in this particular competition. So a lot of good stuff there. All right, so what we're doing here is we've read in our raw data, and again, what I'd like to do is I'd like to just take a peek at the data, see the shape. Okay, so I've got a data frame here of all of the ID variables for this particular data set. So we have two main data sets. So one is variables that pertain to the identification of a particular consumer, and then another data set that pertains to the variables of the various transactions. So when you sort of step through these, you should kind of be thinking in your head, like, do these outputs make sense? So, like, for example, had I seen that our transaction data frame had less observations than our ID data frame, then that would be sort of a red flag, like, oh, maybe I didn't download something correctly. So those are the questions that you kind of want to ask yourself as you're stepping through this code, just to sort of avoid any obvious mistakes. Okay, cool. So then what we're doing here is, now that we have those two data sets, we want to merge them together. So we'll use this merge function for the data frames. So we'll run that, and then again, just want to be continually checking, making sure that we're getting the results that we're expecting. So this will run. It'll take a little bit, but in this train full data frame shape attribute, I'm expecting to have columns that sum these two up here, right? So I'm merging these two data frames on a column basis. So I would expect 435 columns to be coming, or 34 columns to be coming in, and here it is. So that makes sense to me. And then I would expect the number of rows to be the higher of these two, and that being for the transaction data frame. So that makes sense. Okay, that's cool. All right, and then really quick, just sort of take a peek at the number of fraudulent instances that we have in this data frame. So it's roughly 3.5%. That's an issue, and it's very common in fraud detection examples. This low percentage of labels, and it presents an issue in particular because it'll throw off the way that you're looking at the overall accuracy and performance of this particular model. If you have so few instances of fraud, then you can easily get a pretty high accuracy score by not really detecting any of the fraudulent events. So if you detect if you just say 0 for everything, you'll get like a 97% accuracy on this particular model, which is probably not what you want, right? You want to pick out those fraudulent events, but this is an instance where if you just look at the raw accuracy, you're actually going to be misled into thinking you have a model that's better than what you might have. So this is just something to keep in mind. The other thing that we have to deal with is the number of NAs in for this particular data set. So the assignment called to do a visual. So here's my visual, and really I want to look at NAs and the percentage of NAs for all of these columns. So what we're doing here is we're creating a bar chart, and we want our y-axis to correspond with the overall percentage of NAs in a particular column. So we're doing that by pulling out the NAs, doing a count of those NAs, and then dividing that count by the total number of observations in that in the data frame. So this will give us an overall percentage, and then our x axis is really just going to have the name of the variables, and so we can run that, and we'll generate a chart like this. And here, hard to see, I'll zoom in a bit, but here we have 100% NA. So these are columns that are not very useful, at least for me right now. And then columns that are less that have less NAs in them. So we can zoom in here, double click on that, and see which of those columns are the ones that we want to avoid here. So as you move here to the right, these are sort of the ones that are going to be a little bit healthier. Okay, so that's just sort of good, kind of like take a peek at the data, see what's going on. Now, so now getting into cleaning up the data a little bit. So let's make sure we run that, have that handy. And when it comes to NAs, I think there are two basic strategies that you want to consider. First is pretty straightforward. Is just drop all of the NA rows or observations. So what you'll do is you'll say, like, anytime there is an NA in one row and observation, just drop that entire observation and clean it that way. If you have columns where you have 100% NAs, and that's pretty much going to wipe out all of your data, so that's not always best. Another way to do it is to look at the columns that have the highest frequency of NAs and just drop those columns, and then do a drop NA on the rest of the data that's remaining. That's the approach that we're actually going to take. And then another approach would be to recode the NAs. So if for an NA you might fill it in with a hard-coded number, or you might take the medium or the average for the entire column and just have that be the variable for that particular NA. We're not doing that. We're not doing this in this particular instance, but that's another option that you can consider. All right, so let's jump in here. So what we're doing here is we're creating a data frame that is going to give us the number of NAs for a particular column and the percentage of NAs per column. So let's run that and that, and then let's take a peek here at this new data frame that we have. All right, and should give us the column name from our original combined data set, the number of NAs in that column, and the percentage overall. So the question for us is what percentage are we willing to tolerate? So obviously we don't want columns that have near 100% NAs in the observations, but I don't know if we want to be as stringent as saying that we want 0 NAs in that column, because it seems like that'll sort of take out too much of the data, and that's not ideal either. So what's kind of a good way to kind of figure that out? For me, is I cycle through various thresholds, and I see how much I'm going to have remaining and what I'm willing to tolerate. So I'll have a number of ranges and saying, like, hey, I'm only willing to tolerate 5%, 10%, 15%, 25%, 40%, up to 75% of NAs in a particular columns. And then I want to see what percentage of the original columns are going to be left, and that's what I'm doing in this for loop here. So let's run that, and this will tell me, like, hey, if you're only willing to accept 5% NAs in a particular column, you're only going to be left with 25% of all of the original columns. Is that something that you want to go with? And 10%, and then 15% here. So I guess what I'll do is change this to say 15% and say, hey, if I only tolerate 15% NAs in a particular column, I'm going to keep roughly 37% of the original columns. That to me seems reasonable. So let's change this actually here to 15%. Okay, so that's going to be our limit. So now what we're going to do is we're going to identify the columns that are less than that limit and create a list of those names. And then we're going to take that list and we're going to subset from our original data frame to pull out those lists of columns. So we create that here, and then we use this function here, this columns.intersect function, to only pull those columns from this list here. So let's run that. Okay, so now let's actually do another check. I always like to check my data to make sure that I am getting what I expect. So I would expect not that. Okay, I missed the DF here. I would expect to have 25%, or what do we say, 36% of columns in the original data set, and 160. And then if we were up here, I think we showed 434. So 160. That seems in line with the 36% that we had expected. So that makes sense. Okay, so another thing to think about is how to deal with categorical variables. So you're going to have numerical variables. Those are pretty straightforward. And machine learning algorithm will pick those up pretty readily without too much pre-processing. But categorical variables are a little bit trickier because they're either string or they're factors, and it's not always that straightforward for a machine learning algorithm to pick them up. So if we look at some of the categorical variables that we have, we can do that by running this function on the train full data frame. So we see things like product CD, card 4, card 6. So this is the type of transaction, the card that was used. And so what you might want to do is create dummy variables for these categorical variables. So what you'll get is you'll get columns that represent each one of these unique values, and then in that column you'll get a 1 for any time that it corresponds with that particular observation. It's probably just a little bit easier to see. So let's kind of step through that. So here's how it looks like in the original data set. It's card 6, and it's it's either credit or debit, right? So let's create a dummy variable from that. Okay, and we do that by running this function here on that original on that variable. So let's run that. Okay, and then let's add that, and let's see what we have here. Okay, cool. So what we did is from that one variable, we now created 4 variables. So it's so here, if we go back to the original data, we should see that the row would have said credit here. So let's go back here, credit. Okay. And then the third, or the second item here, debit. So we should have a 1 in the debit column here. So 1 in the debit column here. So boom, that makes sense. Okay, so now I've created dummy variables from this variable. Now I want to add this back to my original data set. Okay. So first, what I want to do, however, is I want to drop that. See, I missed that right here, that part. I want to drop that original category. Actually, no, because you're not going to have the same names. So these are charge card, credit, debit, debit or credit, and that's not the same as the original. So I'm not going to have an issue there. Okay, so I don't have to just drop it. We'll drop it later. I'll get to that in a minute. Okay, so then now we have our new dummy variables here, and we have the original data set. So now we're going to combine those two. We're going to merge them using this function here. So let's do that. Awesome. Okay, now what we're going to do is we're going to drop all of the categorical variables and just keep the numeric variables. And because we did this dummy transformation, now our card 6 column is now a numeric variable. And then after that we're going to drop all of the NAs. We're going to drop all of the NAs. So any row, any observation that has an NA in it, it's going to get dropped. And then let's see what percentage of labels we have remaining. So let's go ahead and run that. So 2%. We actually lost a percentage point on the number of labels, which is not great, but 2% is still okay. All right. So now, last steps here is we'll create a data frame for our X variables and an array or a data frame for our Y variables that we're going to be looking to predict. And then lastly, we'll create our test data frames and our train data frames. So, as previously mentioned in another video, what you'll want is a set of data frames X and Y to do your training on, and then a set to do the evaluation and the testing of your algorithm to get a sense of performance for that algorithm. So once we do that, we have what we need to start our modeling process. And the only modeling that I'm going to be doing here is just logistic regression, just keeping it simple, and then just pulling in some libraries to do some reporting. On the performance of the simple logistic regression model. So let's go ahead and run that, and let's set up our logistic regression model. So have that run. We'll take a moment. Okay, cool. So that has run warnings but no errors. That's good. So now let's get our overall score. And wouldn't you see, like, our score looks great, right? The overall accuracy looks great, 98%. So this is actually what happens when you have such a big label imbalance. So this score looks good, but it's likely that it's actually not as good as you would think by just looking at the overall accuracy. So let's create a predictions for using our test, our test data, and then let's compute our confusion matrix. So let's run that. Okay. So what's nice about, so how do you read a confusion matrix? Okay, so let me actually just kind of bring up a good example. Let's see here. So we have predict on top 0, predict no, actual. Okay, cool. So this is a good example here for us. Hey, data school, these guys are good. Okay, so with the confusion matrix, you're going to get a table of your predictions by whether or not you predicted that there was a fraud, yes or no, and whether or not you were correct. So was it an actual no? Was it an actual yes? And when I'm looking at anomaly detection or fraud detection, I'm looking at recall. So what you want to see is a high percentage of overall frauds that your model was able to determine. So here, let's just kind of do the math here on our own just to make sure we understand it. So the number of true instances, the number of true instances in this data set, in the test data set, was roughly 4,400 different frauds that were detected. And of those 4,400, we only got 12 of them. So all these other ones got by us, and there was fraud that was committed. So then our recall is going to be that 12 that we predicted by the overall number of frauds, right? So that's very minuscule recall that we were able to predict. Now, the reason why our accuracy score was so high was because we correctly predicted a lot of the non-fraud observations. But the problem is that those make up a lot of the data, and so you're predicting a lot of those, but you really care about being able to predict these here and getting these alerts. Now it sort of it can depend on what you want to optimize, whether you want to optimize the overall accuracy or your false or your recall rate or your precision. You can do different things to your algorithm and to your modeling process to optimize for those different metrics. But in this instance, my view is that if you're trying to detect fraud, then you want to have what's called a high recall. So that's the way to describe that again, is for all of the fraud events that have happened, how good was my model of picking out those particular fraud events? And then, and this instance is not particularly good, even though I got a high overall accuracy. Anyhow, so if you run that should give me the same number here, which is nice. Again, I like to do the math first and then get it through the function just to make sure that I'm understanding this correctly. And then that we saw earlier, this I think is just the same as that. So we can actually cut this and cut this. All right, so then that's pretty much it. There's a lot more work that you could do to get this score up, but I just kind of wanted to walk through it and talk about some of the things that might seem interesting. What would I do next if I had more time to work on this? There'd be a couple of things that I would consider doing. One is I would work on rectifying the imbalance issue. So I only have 2 to 3% of my overall labels being frauds. There are different sampling techniques that you might use to fix that and to give your algorithm more labels to work with. I'll try to find a link to some good strategies and share that later on. But I'm sure you can Google it and find that out. I can, and the second thing I can do here is decide to drop less columns or to have a higher tolerance for NAs. We can impugn values for those columns into NAs. So instead of just dropping them, so we can replace them with something else. Definitely try other algorithms. I just tried logistic regression. That's pretty straightforward. Others will likely do better, particularly the fact it's fairly high dimensionality, a lot of features. And then the other thing that we could have done too is more hot coding of categorical and variables. Or more dummy variables for those categorical variables that we saw earlier. So those are all things that I would look to do a little bit more if I had some more time to work on this. But anyhow, I hope you found that somewhat helpful, somewhat useful. Let me know what you guys like. Let me know if this is helpful at all. And just keep hacking, guys. Keep at it. See you later.